What is up, everybody? How are y'all? One last time, come over here, make sure that's turned up. Yep, cool. And I did hit record, right? Yes, I did. All right, so we are going to get into section 6.1. This is the week 14/15 slides under exam 4. Before we get into this, though, I just want to make sure y'all are aware there is an exam next week. It will be at the end of the week. So we have the exam at the end of next week, and then the following week there is the final. You will have all week to take the final. The final will be over everything except for chapter 6, just because we've just tested on it. Why test you again? What else? I will make myself available to y'all all week. So if you have questions, you can hit me up and ask me your questions. There are study guides from chapters 1 through 5 available on a WebAssign right now. What else was there I wanted to say about all this? Exam 4, like I said, will be the end of next week. It'll cover everything from chapter 5.4 on. What else? I think that's it. Yes, exam 4 next week, finals the week after. You have all week to take the final. You can ask me questions whenever you need or want. And there are study guides up on Blackboard right now. Having said that, though, let's get into chapter 6.1. So 6.1 is all about what's called integration by parts. An integration by parts is built using the product rule. So what it says is, first, since the product rule of two functions from this point on, I'm going to write as just u and just v. Since the derivative of the product of these two functions is equal to v times the derivative of u plus u times the derivative of v, well, we can rearrange this. We could say that this is equal to d dx of ub minus v d du dv. From here, we have some notation we've used in the past. We're going to use it here. Remember, if you ever see something like du, this thing is equal to du dx. So, with this in mind, applying the integral to both sides, we're going to get this derivative is undone minus the integral of v du is equal to u dv. So what we've done is we've applied the integral to both sides here. Like that. I forgot to write this the rest of the way. Forgot to add that dx on the back there. Okay. So all this integration by parts is really going to be is rearranging the product rule to make a particular integration easier to solve. And what we're going to find is that, let's zoom in on this part right here. What we're going to find is what this integration rule says is anytime you have the product of two functions, you can think of one as being the derivative and the other just being some function. So this is going to tell us that v is equal to the integral of dv dx with respect to x, right? And this is going to tell us that du is equal to d du dx times dx. So by identifying what u is and what dv dx is, we can plug them into this left side here and possibly form an integral that we can solve. Make sense what I mean? Everybody cool with this? So this is a really abstract idea. It's not immediately obvious how this gets used or what it's doing. Not until we actually see it in practice. So let's put it to use. First, the next couple of slides are really just the integration by parts definition, as well as some guidelines for integration by parts. But because this is such an abstract idea, I personally don't like guidelines for this. I've never found a set of rules that I thought were concise and descriptive enough to actually help. So instead, I think we should just jump right into a problem. Okay. So for this first example, we have the integral of x e to the x dx. Now we have a couple of different possible candidates here for what our u's and our v's are going to be. U could be x, u could be e to the x, you could also be x e to the x. I'm actually going to do this even more spread out. Let me do it like this. Equal to e to the x. U is equal to x e to the x. Okay. If u is equal to x here, then dv, that's going to have to be e to the x dx. If u is equal to x, or e to the x here, then dv is going to have to be x dx. And if u is equal to x e to the x, then dv is going to have to be dx. if u, coming back to that first example, is x, then du is just going to be dx. If u is e to the x, then du is e to the x dx. And if u is x times e to the x, then du is going to be x e to the x plus e to the x dx. Okay? Now, if dv is e to the x dx, then b has to be e to the x plus a constant, but we don't need to worry about the constant for right now. If dv is x dx, then b is equal to 1/2 x squared. And if dv is equal to dx, then b is equal to x. So up to this point, what have we done? We've just said, all right, based on our integrand, what are our candidates for u? We had 3. Then we said, all right, based on those 3 candidates for u, what are our candidates for v? It's whatever's going to remain times dx. Okay? Based on that, what's our vu going to be? And then what is our v going to be? Now, looking at these, we want to take advantage of the fact that u times v minus the integral of v du is equal to the integral of u dv. So this is what we started with, right? The integral of u dv. What we're aiming for is for this integral to be something that we can work with. So which of these combinations will lead to something that the integral of v du is solvable? The first candidate looks like the best one, doesn't it? Because if we use it, then we're just integrating e to the x. The second candidate, we've increased our x by a power. The third candidate, oh hell no. That is not easier. We don't even want to try. So, first candidate it is, right? What this tells us then is that plugging in u, we get x, right? Plugging in v, we get e to the x minus the integral of v e to the x du dx. Well, this we can solve now, right? This is going to come out to be the integral, or my mistake, this is going to come out to be e to the x plus a constant. So our answer then is e to the x minus e to the x plus a constant. And you could write minus a constant, but really you're only changing it by a constant. So plus or minus that constant is still the same. So what we just found was that the integral of x e to the x dx is equal to x e to the x minus e to the x plus a constant. This is what that question of the week last week was about. It was about how do we start thinking of the product rule as a tool, not just for derivatives, but also to set up some useful integration techniques. So, comparing answers really quick. They, like me, decided to be a little extra here and consider every possible combination of U and dV. They went one step further and said, we have even more than just what I wrote up here. They considered a dV, or x e to the x dx is equal to dV, right? Then they said, of these, which one's going to give us something useful? Using that, let's set up our integration by parts and solve. So by identifying your U's and dV's, you then can identify your dV or your V's and your dU's. Then you can start setting up those integrations. And after a little while, after a few of these, it actually becomes pretty quick. Yeah, this method of considering every possibility sucked. After a certain point in time, you won't have to set this up like this anymore. It'll be pretty obvious which ones to go with. Just like after you factor stuff out for a while, that gets a lot quicker. Same idea. Okay, so in this next example, we've got something that at first we might think we could apply some sort of U sub method or something to it. Like honestly, looking at it, that's my first thought would be U sub and some sort of an ln trick. But nothing works here until we apply integration by parts. So starting off, we got the integral of x squared ln of x dx. Now, as our candidates U's and V's, for U, we can have x squared, we can have x squared ln of x, we could have ln of x, we could have x, we could have x ln of x, right? Like we could have a bunch of different possible candidates for U here. We actually have three factors. 2 x's and 1 ln, right? But traditionally, one of the things we'll like to do is if we have like an x squared, keep it with its power. Don't try to break up that x. Not unless it's obviously the result of a derivative. If it's that case, then break it up. But for right now, let's keep our x's together. That actually sounds like a really bad idea. Never keep your x's together. They just cause fights then, right? That was a dating joke, and it really did not land. I'm sorry. Okay, so if U is x squared, dV is going to be equal to the ln of x dx. If U is equal to x squared ln of x, then dV is equal to dx. And if U is equal to the ln of x, dV is equal to x squared dx. Going back over, du, well, that's going to come out to be 2x dx. over here, du is going to be x plus 2x ln of x dx. And then here, du is going to be 1 over x dx. So over here, v is going to be the integral of the ln of x dx. Over here, v is going to be x, and here, v is going to be 1/3 x to the third. We don't like that du. It got messy really quick. We don't like this v. We're going to have to apply integration by parts again. So let's ignore that one for now. That leaves us with this. So coming back over to our original integral now, we chose u to be the ln of x. V is x to the third over 3 minus the integral of v x to the third over 3 du is dx over x. We have a simplification now, right? We can lower this by a power. So we have the ln, we have 1/3 the ln of x times x to the third minus the integral 1/3 the integral of x squared dx. So now, solving, we have 1/3 the ln of x, x to the third minus 1 over 9, x to the third plus a constant. So checking our answer really quick. You have dv equal to x squared dx, u equal to ln of x. That's what we chose, right? Yes. So if that's the case, setting up our integration by parts, it's this first little bit we have in orange. Simplifying it, that's the second bit that's hard to read. Then once we integrate it, we got 1/3 ln of x times x to the third. Okay, looking good so far. Minus x to the third over 9 plus a constant. Same thing, right? So far, everything seems to be making sense, right? It doesn't seem like this is just particularly difficult. It's more tedious than anything, right? Now, up to this point, we've been avoiding setting our dv equal to dx. Here we're going to do that. Whenever you have just one factor in your integrand, your dv is going to have to be dx. I probably shouldn't make that generalization because I'm sure there's a counterexample, but it's a pretty decent generalization for right now. So here we're setting, let me rewrite this, ln of x dx. Here we're going to set u to the ln of x dv equal to dx. So du is going to be 1 over x dx, and v is going to be x. So applying all of this now, u is the ln of x, v is x minus x times du over x dx. This can be rewritten now as the ln, my mistake, as x ln of x minus the integral of dx going to come out to be x ln of x minus x plus a constant. Again, we generally don't like to use, oh wow, I have a huge typo up here. It should have been x. We generally don't like to use dv is equal to dx unless we only have one term. I'm trying to think of other examples and none are really jumping out at me. Yeah, none are really jumping out at me. It's just like we generally don't like to set u equal to 1 unless we absolutely have to either. But there are very rare cases where either of those happen. They do happen, but they're not that common. So don't throw them out immediately, but don't jump to them, is what I'm saying. Like, don't let those be your first assumptions. Folks at home, does that make sense?
Yeah.
All right. So, really quickly comparing answers, we got the x of ln, or x times the ln of x minus x plus a constant. We got the same thing. We got it by going through the same method. Now, having said this, not every integration by parts, not every integral can be solved by one application of integration by parts. Sometimes you have to do this iteratively. So for example, let's say we have x squared e to the x dx. This is a problem you're going to have to apply integration by parts twice. Here's that example actually worked out. So the first time you're going to apply it, you're going to have u is equal to x squared, v is going to be e to the x minus the integral of d e to the x du is going to be 2x dx. Well, got to apply integration by parts again. Got to apply it on this guy now. So we're going to have, from this point, x squared e to the x minus, we can pull out our 2 and rewrite this as the integral of x e to the x dx. Now this is going to be x squared e to the x minus 2 times setting u equal to x, d equal to, or dv equal to e to the x dx, will give b is equal to e to the x minus the integral of d e to the x du is going to be x dx, or I mean, my mistake, it's just going to be dx. So now we're going to get x squared, let me write this in a different color, x squared e to the x minus 2 times x e to the x minus e to the x plus a constant distributing that -2 all the way through now. We have x squared e to the x minus 2x e to the x plus 2 e to the x plus a constant. And now we can factor out the e to the x if we really wanted to get x squared minus 2x plus 2 times e to the x plus a constant. So here is integration by parts the first time, right? Here is integration by parts the second time. Notice what caused us to use integration by parts was this integral and this integral, right? Both of which are of the form x to the n e to the x dx. Anytime you see an integral show up of that form, you're going to have to apply integration by parts n many times. So in our case, n was 2, integration by parts once, integration by parts twice. We did it n many times, 2 times. So just for something to look out for, integrations of this form, you're going to have to do integration by parts n many times. And just as a a healthy practice, it's always a good thing to go back and see if you can find patterns like that in your homework problems, because it'll help you solve future homework problems, right? Like that odd and even idea. The same way odd functions and even functions help to reduce some homework. Making note of observations like this will do the same thing. So having said that, another question might naturally occur at this point. How do we use this with definite integrals? Because it seems a little weird to pass those bounds through to UV. So what I mean is, we have something like this. How are we going to pass these bounds through? Well, this comes back to what I was saying when we first started talking about definite integrals. I said, after I do the integration, I like to use a square bracket with the bounds as superscripts and subscripts, right? And the reason why I like this notation is because when we use integration by parts, it's natural to want to close this and say, apply it to the whole thing. Make sense what I mean? So I feel like this square bracket is a natural notation for this reason. And having said that, looking at a definite integral that has to be solved using by parts, we've got the integral from 1 to e of the ln of x, integrated with respect to x. Well, we just saw that integral comes out to be the x ln of x minus x, right? Now, keeping our bounds, we're going to do this from 1 to e, right? Now we're going to come back and we're going to say, all right, cool. All this means now is I'm going to have to plug in 1, and I'm going to have to plug in e, right? So plugging in e, the ln of e, minus e, that quantity, minus 1, the ln of 1, minus 1, going to be e times 1 minus e minus 1 times 0 minus 1, going to go to 0, and these are going to cancel, so we're going to be left with negative 1, or just 1. So really nothing changes in principle, right? All we're doing is we're coming over and saying, all right, let's close off that square bracket. That way we know down the line to do to apply the bounds to the entire result, right? Having said that, just to break this up a little bit more and show it in detail, what I've done is I've said 1 to e ln of x dx is equal to x ln of x minus the integral of dx from 1 to e. Right? And then I did that. So just to kind of show what actually happened before we got to this point, we actually did that integration, right? So yeah, integration by parts. That's it. Just as some observations, some more observations that are worth noting. Notice these integrals really only differ by powers, right? The first integral to the second integral, x differs by a power, right? Here we have x to the first power, x to the negative first power. From here to here, it's only ln of x that differs by that power. In this first example, we're going to use integration by parts. In the second example, it's going to do the power rule. Then in the third example, it's going to do the log rule. That is, of course, after we apply u sub, right? So very similar integrands can require very different techniques. And for this reason, like I said, don't like going off with just simple guidelines. I don't think there's a guideline that really prepares anyone to think about this in a way that will recognize and distinguish between each of these possibilities. That said, you can apply integration by parts everywhere. If you really wanted to, you could solve all of these problems with integration by parts. Wouldn't suggest it. Integration by parts is a little cumbersome, but you could apply it everywhere. However, you can't apply the log rule or the power rule everywhere, right? So just some things to be aware of. Integration by parts will always be applicable. Power rule, log rule will not always be applicable, but they may be better techniques to use than integration by parts, right? So just know this in advance. Having said that, two really common examples of where you're going to use integration by parts. X to the n times a thing, either e to the ax or the ln of x. These are two really common examples. Having said that, something to note on, in this first example, like I said before, you're going to have to apply integration by parts the same number of times as x is raised to a power, right? So n number of times. But in the case of x to the n ln of x, you don't. And we can see that over here, actually. See that over here because what's really happening it'll be easier if I actually draw out the entire example. So let's say we've got x to the n ln of x dx. Right away, set u equal to the ln of x set dv equal to x to the n dx. This is going to tell you du dx is equal to 1 over x dx, and v is going to be equal to 1 over n plus 1 x to the n plus 1. Now look what happens when we apply all of this. U is the ln of x. V is 1 over n plus 1 x to the n plus 1 minus the integral of x to the n plus 1 divided by n plus 1 times dx over x. So what we have then is x to the n plus 1 times the ln of x divided by n plus 1 minus 1 over n plus 1 times the integral of x to the n dx. We can solve this using power rule now. It's going to come out to be x to the n plus 1 times the ln of x over n plus 1 minus 1 over n plus 1 n plus 1 over plus 2, right? Times n, my mistake, I miswrote this. It's supposed to be 1 over n plus 1, that quantity squared, times x to the n plus 1 plus a constant. So you have to apply integration by parts in many times. You have to apply integration by parts once. Having said that, this actually leads into our next section pretty well, which is going to be using integration tables. Because now, anytime we have an integral of this form, we now know any integral of this form will look like x to the n plus 1 times the ln of x over n plus 1 minus 1 over n plus 1, this thing squared, x to the n plus 1 plus a constant. Now, anytime we get an integral of this form, we just have to know what n is, and we can figure out pretty quick just by using this what the integral will be, right? So, as an example, x, let's use something ridiculous like 100. ln of x dx is going to come out to be x to the 101 ln of x over 101 minus 1 over 101 squared x to the 100 first power plus c, right? And all we had to do here was identify what our n was. This is what it is to use a table of integration. You get your integral into a form that the table is written in, and you apply what's in the table. That will be what's in the next section. But before we get to that, we have this idea of present value and actual value. I find this particularly difficult to explain and to even understand because language really sucks here. Actual value is what your bank account reads. Present value is what we're looking off into the future. You get $1 a day. $1 a day for a year, $365 by the end of the year, right? But by the end of the year, interest rate has devalued those dollars a little bit compared to what they are today. So looking at what's in your bank account ahead of time, it will read $365, but the value of those $365 will be the present value. So it's looking at what it's worth in today's money based on what you think you'll have later. Makes sense? So this is one way of comparing like buying power, right? Just because I have $1,000 tomorrow doesn't mean that what I want to buy tomorrow will be worth $1,000, right? It's going to be more than 1,000 because of inflation. So that means that $1,000 tomorrow is worth less than what I think of it today. Cool. That's the difference between actual income and present value. Actual income is what your bank account reads. Present value is what it's worth in today's money. But having said that, we are 5 minutes over. I didn't realize we went that far over, so I will let you all go. Check out this problem while you're at home. We're going to go over it pretty quick next class. And I anticipate Monday we'll go through most of the remaining slides. Wednesday will be half the day just review.